Hello guys, in this video we will learn about persistent data structure. So let's start with all the definitions. A persistent data structure is a structure which preserves its previous version. For example, when you make any update or any write on a data structure, you create a new version and preserve all the previous versions of it, which can be accessible as well. Such a data structure is called persistent data structure. It is called a partially persistent data structure if all the versions can be accessed, like read only option is available on all the previous version, but only the newest version can be updated. Then it is called a persistent data structure. A fully persistent data structure allows you to read and write on all the versions, all the previous as well as the new version. It allows read and write on all of them. A confluently persistent data structure is a structure where you can merge one or two versions to create a new version. So let's say you have three versions, version 1, version 2, version 3, and you created a version 4 by merging version 3 and version 1. Such a data structure is called confluently persistent data structure. So let's understand now different ways to implement such data structures. So first method is called fat node. In fat node, instead of creating new versions of the nodes, we store all the modifications inside each node itself. So we don't copy the nodes and everything, we just store the version information inside the nodes only. So this allows partial persistence because you can access the previous versions, but it's very difficult to make any changes in the previous version because we are not copying any nodes, right? We just manage the versions inside the node itself. We will look into the example below. So let's say I'm taking the example of segment tree here. So in a segment tree, you usually have a value, a left pointer and a right pointer. So if you are not aware of the segment tree, you can check my video on segment tree, then come back to this video. So a segment tree has all these three fields, right? So in a fat node implementation of a segment tree, instead of value, we will just maintain a list of values and the versions. So we will maintain a list of mappings where each mapping will have a version and the value that represents that version. So similarly we will do for the pointers as well, left and right pointer. So whenever we change any pointer, right, for example when we add a new node or maybe restructure the tree, so the pointers will change, right? So instead of changing the original pointer, we will just maintain an array of left and right pointers and we'll just insert new entry there. So let's understand it by looking into this example. For example, you have an array of 1, 2, 3, 4. Now if you will create a segment tree on this, it will look something like this. So all the array values will be at the bottom, 1, 2, 3, 4, and the parent nodes will have the sum of these values. I have created a segment tree based on the sum of the array values. So segment tree will look something like this. So as you can see, each node has a key value pair. So this represents that is the version 0 or version 1. You can take 1 as by default, but it's the version 0, and what is the value of that node in version 0. So the root node in version 0 has value as 10, and same for others. Now let's say if you want to update index from 1 to 5, so we want to update this 2 to 5, then how will it look like? So when we update this node to 5, you can see instead of updating the previous value, I'm just inserting another entry here. So now this node says in version 0 the value is 2, but in version 1 and the new version the value is 5, and hence if the root node in a segment tree changes, the value on the parent nodes also changes. That like the value of all the nodes that belongs to this path will change, right? So as you can see, new entries are inserted into all the nodes that belongs to this path. So here as well, as done in the new version, the sum will become 5 plus 1 6, right? So the new entry of version 1 and value as 6 is pushed into this node. Similarly, the new sum of the array will become 13, right? So a new entry with version 1 and value as 13 is pushed into the root node itself. So as you make new updates, these nodes become fat. By fat I mean more entries will be getting inserted into the nodes, right? So these nodes will like expand and become fat. That's hence the name fat node. So benefits here is we don't need to duplicate anything. We don't need to copy the nodes here. Like we just push entries into the nodes itself, and version is managed by the node itself. So there is no node duplication, hence it saves some space, because the only extra space you are taking here is for this version number, right? That's all you need. So it's space efficient when updates are rare, and querying older version is easy here as well. So if you want to query any older version, you just go to the node, and in this mapping you just pick up the version you want, right? So here you can store a map instead of array or something. That will be that will make it easier to pick up a version. So here it's partially persistent, read any version, because only the latest version you can change. You cannot do the writes on the older version, because we are not copying the nodes, right? We are just pushing everything into an array. So it will, whenever you push anything into array, it will sit on the top of the latest version, right? So it will be treated as a newest version every time, and it will be treated as a update on the last version only. So for example, here we have 0 10 1 3. Now if I make any update, an entry will be pushed into it on the top, right? So if you will look in terms of array, it will look like first the value was 10, then 13, then some other value. So you cannot make changes into the older versions, so hence it's partially persistent. So limitations, version list grows with updates. So same thing, as you make more updates, these nodes will become more fat. Harder to implement full persistence, I've explained it above as well. And access time is not a strictly order of log n. So it depends actually how you store these information into the nodes. So if you will use map to store these version and this value mapping, then the time will be less. But if you will store array, for example, uh, let's say you have made 10 updates, so here will be 10 entries in this node, right? So when you will make a read or something, you have to go through these 10 entries and find out your specific version. So the access time is not actually login. You will be taking some more time to find out your version in each node. So in each node you have to get the values for that particular version, right? So the access time is not exactly login. It will be a little bit more depending on the implementation. So we should use it when the updates are not frequent. So when the updates are rare, and you only need to access older version, but always you need to write the latest version, then you can use this node. And you want a space efficient approach. Okay, let's move to another approach, which is node copying. So in the node copying approach, whenever an update is made, we copy the affected node, and the rest of the data structure is used as this is typically used with immutable nodes. For example, when you want to when you don't want to modify a node, so here the nodes are not immutable, because you are making changes in the same node itself. You're not copying the node. But if you want immutable nodes, you have to go with the node copying. So it doesn't work well in trees. It usually works with simpler data structure, like linear data structures like stack, queue, and functional languages. So stack, queue also it works with only when they are implemented using linked list. It's easy to use node copying in stack and queues when their implementation is done with the linked list. So let's take an example on stack itself. So in this approach, let's say initially we have a null node. So let's say a stack is empty, right? So I'll just represent it by null. So initially in the 0 version, a stack is empty, hence the null. So let's say we are pushing a value of 10, which will in the version 0, which will create a version 1. So as soon as you push a new node, another version will be created, right? So in the version 1, the root pointer, the head of the stack, will be 10. As depicted in the as you can see in the diagram, the head is 10 now. Now if you push 20, another version will be created. Now the head in the version 20 will become version 2 will become 20, and in the version 1 the head is still 10. Now push 30, same thing, another version is created. Now we want to pop version 2, and we want to that will create a version 4, right? So this will create a version 4, right? So if you will pop in the version 2, for example, version 2, the head node is 20, right? So if you will pop the stack from here, your stack will be like 10 and null, right? So imagine if you don't have 30, for example this thing. Now if you will pop 20 out of here, all you is left with 10 and null, right? So in the version 4 you will just uh, put a pointer reference. So version 4 will point to the 10. So as you can see, you are not actually deleting a node here, or actually not removing the node in the list, right? You are just maintaining a reference. So is version 0 says null, but for version 4 points to the node 10. So you're just just storing the reference to this node. You're not actually making any deletions or any update in the stack. So the data is still same, as you can see from the last diagram, but only the reference you are making here. So now in the step 5, let's say on the version 1 you are making an update. You are pushing the value 99 on version 1. So as version 1 points to node 10, when you push it here, you just create a new node with value as 99, and you point it to node 10 and store a reference of it in version 5. So now version 5, the stack is 99, 10 and null, and version 4 the stack is 10 then null, and in version 3 the stack is this linear array 30, 20, 10 and null. So that's how you implement node copying. It's basically like reusing all the nodes that are previously created. We are not making any modifications in the nodes that we have created previously. We are, for every version, we are just creating a new node and storing a reference to it. And in case of popping, we just go to the root head node according to our references, move the pointer one node ahead. For example, if we were on 20, we just move the pointer to the next node and we store its reference in the next version. That's all we are doing. We are not making any modifications in the node, hence the nodes are immutable here. So benefits here is it's like simple and efficient. Like as you can see, it's really easy to implement. Only just need to store the mapping somewhere. So you need to maintain an array or a map to store all the references for different versions, right? So this you have to do manually. This is as in this fat copying node, the version history was maintained by the nodes itself, right? You were not storing any map or something, but here you need to keep track of the all the versions explicitly by using a map or an array or something like that. But it's simple and efficient. Only copy what's necessary, and typically it's like it takes order of one time in stacks. Like so you can see here we are not taking extra time. We are not iterating over the whole stack. We just go to a reference pointer and do our operations. Order of one time in stacks and order of login in tree if you do something like this in tree. Reuse of old nodes. We are not creating new nodes every time whenever we're making changes. So it avoids duplication, saves memory, and all the older versions are accessible for read and write as well. So as you can see, you made an update in the version 1 here, right? So all the versions are available for read as well as write. So it's full persistent approach. So it's also enable branching, the same thing, full persistency is available here. So limitations here is it will not work alone in trees. So in trees, as you can see, if you go to the fat node example in tree, so if you will copy a node here, the value of the parent nodes is also changing, right, in the persistent tree. So you cannot just copy the node you are making update to. You need to copy everything that comes in the path. This is another approach. We will just look into this approach next. So just for now, just understand it doesn't work alone in the tree. You need to copy all the ancestors. Hard to track reverse uses. So nodes don't know which versions point to them. So as you can see, nodes are not aware, right? For example, in this node 10, there are two versions that points to this node, version 1 and version 4. So there are multiple versions that can point to the same node, and so there is no reverse tracking you can do in this kind of approach. So an efficient and deeply nested data structure. So when the structures are deeply nested, for example, large trees or graphs or something like that, updating a node may lead to updations on other nodes, and you may need to copy all those nodes, right? So it becomes expensive there. Hence, we use this in mostly simple data structures like stacks, linear, linked list, and all those things. So you have to manage versioning on your own. Yes, as you can see, we are storing a map of all the versions here, so you have to do it on your own. So you can use it when working with linear or shallow data structures like stack queues and all. Try you can also use it, but with shallow updates, and we usually combine two strategies there: fat node and node copying. So we put some limit on fat copying, like we can push into the node up to 3 updates, and after that we'll just copy the node with the latest update. So we combine these two strategies in try. I'll explain that in some other video in detail, or you can just research on it. So when you want full persistence or space efficiency, you can easily you can go with this approach, and you are okay with manually managing versions. These are all use cases for it. Now let's look into another approach, which is path copying. So this approach is usually used in trees like segment tree and BST and all. And when you make any updations, deletions, or when you want to work with the tree and want a full persistent, you go with this approach. It's basically like node copying, but in trees you just need to copy the whole path, as I explained here, right? So this is another name is given to it as path copy. So here all unchanged part of the trees are used. So we don't create the whole tree again and again here. We just copy whatever is getting updated, and we just reuse the unused part in the new version itself. So let's look into this example first. So suppose you, again I've taken the same example here of the segment tree, and the same segment tree I have built here. So initially the segment tree will have values in it. So as you can see, the initial layer segment tree is this, and I have represented the pointers with different colors. So the left pointer I have represented with the blue color, and right pointer I have represented with the red color, just to explain this diagram. So initially our tree is this. It doesn't contain any version history. This is a mistake. The initial level tree look like something like this. Now if we update index 1 to 5, the same update we will make as we did in fat copying, fat node strategy. So whenever you make an update on index 1, which will update this value 2 to 5, so you come to this node while traversing a path, right? So first you go to the root node, then you go to 3, then you come here, right? So whenever you make an update, you create a new node out of it. So instead of updating this node, we created a new node which is with the updated value, which is 5, and then we traverse back. So as if you look into the implementation of persistent, if you look into the implementation of segment tree, you use recursive approach to do this, right? So after doing the operation, you automatically go back to the parent node and so on. So after making an update here, creating a new node, you just go back to the parent node, and you create a new node for it, for this as well. So we have created a new node for parent and store the updated value here. So as you can see, the sum will become 5 plus 1 6, right? So we are updating this, we are storing the updated value here. Then again go back to the root node and create a new node for it, and store the updated value here as 13. Now if you will look into the pointers, how the pointers are getting updated. So this tree, the older version, the previous version, it is exactly same as it was before, right? So there are no changes made into this. But if you will look into this this right part here, it's pointing to the previous version. So for example, in the root node, the previous left node, in the previous version, in the first version, root node left pointer was pointing to 3. Now in the new version, root node's left pointer will point to the new node that we have created, which will point to 6. But as the right pointer will still point to the node 7, here we are not copying node 7, we are just pointing its right pointer to the node 7 here, which is like being reused in the first version as well as in the second version. So all this subtree, all this right subtree of this root node is being reused in both the versions. Similarly for this node 6, here only the right pointer is getting changed, right? So modifications were made to the right. So the right pointer will point to the new node, which is 5, but the left pointer will still point to this original node, which is 1. Hence all the subtree which if let's say if there was a tree below this node 1 as well, this whole subtree will be reused in both the versions. Hence the name is there node copying, because we are copying only the nodes that belongs to the path of updation. We are not doing anything with all the other nodes. We are just pointing our pointers accordingly in both the versions. Here also, if you can see, like, you have to manage your versions on your own. So like in fat node, we were storing the version inside the node, right? Here we don't store versions inside the node because we don't need to. We are copying the nodes on the new version, right? So you need to maintain a mapping here as well. For example, your version 0 will point to this root node and your version 1 will point to node 13. So whenever you want to read from version 1, you will just go to this, you will treat this node as a root node and do all your operations. Like, it will work as like a normal tree. And when you want to do any operations in version 0, you will treat this node as your root node. So benefits here, the time will be same, which is we go off log in all the versions, because we are not maintaining a array or map inside the node. So whatever version you want to access, it will take the same time, which is log in. You can access any version anytime, and you can change any version at a time. So here again, if you want to modify anything into the version 0 itself, for example, now in the version 0, instead of making update of 2 to 5, you want to update it to 4, you can just again copy the whole path and with the updated values and make it a version 2. So you can access all the versions anytime, and you can do all the operations on any version. So it provides you full persistency. It's great for the problems like undo operations, persistent queries, and functional programming scenarios. So for example, you made some changes, you want to undo, you just shift back to the previous version. So it's great for these types of operations. Limitations here are more memory uses, because you are actually copying the node, you are actually creating a new node, so more memory will be used, and harder to implement full persistence here. So you have to maintain, you have to keep track of all the versions, and you have to tweak your implementations of the trees to manage these pointers. So whenever you go back to the parent node, you need to copy the node, then shift the pointers accordingly. So a pointer will go to the updated node and one pointer will go to the previous node. So all these things make it harder to implement. So you cannot modify in place, all changes go to the new version. So in fat node, we were modifying in place, right? We were just not copying the node, but all the changes, any change you make here, it will just create a new node. Yeah, and you need to store the mapping of all the versions. So you use it when you want to maintain a history, query past versions, and undo operations when you want to do undo operations, and your system doesn't allow mutations. So here we are not doing any mutations, right? We are for every change we are creating a new node. And when you want mutation, when you don't want mutations and you want efficient updates, you can use this type of approach. Now let's look into another approach, which is nodes with boxes. So this method was given by Slater and Tarjan and their team, and for a tree it involves using a modification box. So let's look into what we store in the node first, then I'll explain using this example. It's a bit complicated. So we'll start with the empty BST. As you can see, starting with the empty BST, you insert value one by one, 10, 5, and 15, and then update a node to change its value. And we use modification boxes to track changes. Let's look into this example to find out what does all these steps mean. So for this example, so whenever you implement this approach, you first decide on the size of a modification box. So modification box, you can just treat it like an array. So you need to decide the size of that array. So here, for simplicity and for simplicity of for explaining it properly, I'm just taking the size of modification box one only. But in real world scenarios, you don't take it as don't take the size as a one. You generally start with 3 or 4. So the box here will so each this array, it will be an array of objects, and each object will store the version, what version the change belongs to, and in what field the change has happened, and what is the new value for that. So let's take an example here. So initially we have a root node with value 10, left and right pointers are null obviously, and the modification box is empty. Now and this we treat as a version 0. Now every change here will create a new version, right? So let's say we are inserting 5 here. Now when we insert a 5 here, it goes to the left of this node, right? So let's take we are trying to create a BST here. So it will go to the left of the 10, right? So I'm again representing the pointers using different colors, again left blue and right with the red. So here, instead of making changes in the left pointer here, we just store whatever we are modifying in the modification box. So here we say now this is a new version, and we are making change in the left pointer, and now the left pointer will point to node 5. So this is the reference to this new node, and we create a new node with value 5, left null, right null, and modification box empty. In the step 2, now we insert node 15. So here if you will look into this version, so in this example I'm just making all the updates in the previous version itself. So now here if you will store the node 15, it will just go to the right, to the right of this node. So what we do here, we create a node 15 with value 15, left and right null, and modification box empty. But here if you will look into the previous example, as we have taken the size of modification box as 1, our modification box is already full, right? So we cannot add another entry here. So as our modification box is full and we are making any update in this node, we have to create a new node. So as you can see, I have changed the colors here. So whenever I will copy a node in this example, I'll just change the color for this box. So here I have made this purple just to indicate that this is a new node which we have copied from this node, and this is not the same node. So when we copy the node, what we do, we just go to the previous node modification box and we apply those changes. So now we created this node from this previous node, so the value is still 10, left is null, right is null. Now this modification box says the left pointer points to node 5, so we will apply this change into the new node. So here in the new node, left pointer points to node 5, right is still null because in modification box there is no operation for right. And whatever the new change we are making, which is like pointing the right pointer of this node to the new node we have created, which is 15, we will just put it into the modification box. Okay, so here the new node, the new root node will look something like this, with the value is 10, left pointer points to node 5, right is null, and the modification box contains the new change, which is pointing the right pointer to node 15. Okay, so now in step 3, let's say we want to update the node 5. We want to update the node 5 value to 5 to 8. We're not insulting the node here, we are just updating the value of node this node to value 8. So we come to this node, we go here, and we see in the previous version the modification box was empty, right? So we will just put the entry in the modification box, no copying is needed. So version will be 3, and the field we are changing is value, and the new value is 8. So here as you can see, when we copy a node, it does not change the old node. So this node will still have a modification box as v1 left node 5. So this will still be the same, only the changes will be in the new node that we are copying. That's what I have written here actually. So here again, version roots must be stored separately. So as you can see, we are not storing all the versions in a node, right? So here only information is about version 2, and here we have version 3. So each node may represent a different version, right? So for root node, we have to store a mapping here as well. So as you can see, our initially our version 0 was this. If I go back, our version 0 was this. Then our version 1 was this. So version 0 and version 1 will point to this node. So whenever we make any put an entry in the modification box, we don't copy the node, right? We just modify the same node. So if the version 0 is initially pointing to this node, and in the version 1, when we made a when we push an entry in the modification box, we change this node only, right? So, and version 1 will point to this node itself. As we are mutating the node here until the modification box is full, both the version 0 and version 1 will point to the same node which has this entry in the modification box, and that is what I have put here. So root 0 root I'm just representing version using this root. So 0 and 1, both the version will point to this same node with the modification box. Now version 2 and version 3 here. So as you can see, version 2 was this. When we copied the node and we made a new entry in this, we applied the entry in this modification box in this node, and we pushed a new entry here, right? And in the version 3, when we make update into this node was still same, right? So version 2 and version 3 will point to the same root node. So these two nodes are exactly same. They are not copied. So as the color is same, they are not copied. They are exactly same, and the same reference is put in this mapping, version 2 and root v2 root v2. Now let's make another change into this tree. So let's change the value of this node from 8 to 20. So we are making changes into the latest version. Now we are changing the value from 8 to 20. So as you can see, our modification box here is full, right? So we will copy this node. Hence we are changing the color. Now we copy the node. We copy all the values from here, 5 null null null, and we apply the modification box changes. So modification box change says update the value to 8. Hence we have putting the new value here. Left and right are still null, and modification box we will push the new change we want to make, which is updating the 8 to 20. So hence in new version v4 value is 20. All the other things remain same. As you can see, this there is no change in this node. It's still black with both the left right pointers null and all. And but you see there is a change in this root node, right? Why is that? Because we are copying the node here. So if I go back in this scenario here, so here we were not copying the node, right? We were just modifying the same node. Hence the left pointer of this root node was still pointing to the same node 5. But in this case, as we are copying the node, right? So this is a new node. These two are not the same nodes. So in this new version, we have to change root node as well, right? So now the root node in this version 4 will point to this new node, the green node, right? So we need to change root node as well. So our previous root node was in the modification box was full in the previous node, right? So we will copy this node as well. So copying this node leads to copy of this node as well, because modification boxes were full in both the nodes. So we create a new node again with the new color, brown color. We update the values from here. We take the value 10, node 5, right null, and apply the modification box change. So the new node will have value 10, left node 5, right points to node 15, and we will push the new update in the modification box. So in the version 4, this node will point to this new green node, which is node 5 dash. I'm representing this new node by 5 dash. And the right part will still remain the same. There is no changes here. Now let's say we update the value. Again update the value of node 5 to node this value to 30. So again the modification box is full. We create a new node, and as we are creating a new node, the left pointer here will change, right? So hence the modification box of our root node is also full. So we create a new node for root box as well, and similar changes we will apply. So we will just copy these things here, and we apply the changes of modification box. So left pointer will point to node 5 dash, and we push the new entry into the modification box. So this node, let's say we are representing by 5 double dash. So in the modification box we say in the version 5 left pointer will point to node 5 double dash. So here I'm just showing the mapping after all these modifications, how the mapping of all the versions will look like. So in the root 0 and root 1, they will point to the same node, root v1, which is black color with the modification box. So which is here, this one. Root 0 and root 1 will point to this. Similarly, version 2 and version 3 will point to this purple node. Version 4 will point to this brown color copy, which is this one, and version 5 will point to this orange color copy, which is orange color. So I'm representing it by color. Now let's see how you read the different versions here. Let's say you want to read node 5 in version 1. So our version 1 represents in version 1 our root node is this one, black color one, right? So we go to this root node of this version 1 and left pointer. So let's go to this version 1 root node, which is this. Now in this version we go to the left because we are representing a BST here, right? So we go to the left, we see the modification box is empty, hence the value of this node is 5 in version 1, because we are not seeing any changes in the modification box. Now let's try to read in all different versions. Let's say we want to read the same node in version 2. Now how we will do it? So in the version 2 we will just go to the new copy. So version 2 we'll go here. So as I have said earlier, these two nodes are exactly same. Both the purple, they are represented by the same color, right? So they are exactly same, and we make until our modification box is full, we make changes in the same node. So both the version 1 and version 2 and version 3 will point to this node. So we will come to this node. So when we are reading this box value, this node value in version 2, we will come to this node. We see we have to go to the left. Now here it says the right is pointing to node 15, left is still pointing to the node 5. So as we in version 2, if we want to read right, we will not take this right as null, because we have an entry in the modification box which says version 2 will, in version 2 the right will be pointing to node 15. So if we were reading this node, we will take this entry. But here for left, as there is no entry in the modification box, we just go to this, which is node 5. Here we say here we see in the modification box there is an update for version 3, but we are reading version 2, right? So version 2, so we will just send the value of version 2 as 5, because we don't have a entry for version 2 in the modification box. So we'll just take whatever value is present in the node. Now let's say if we are reading it for version 3. So version 3 will again come here, we will again go to the left. Now here we have a modification box, we have an entry for version 3. So instead of sending the value 5, we will send whatever we have in the modification box, which is 8. So that's how the read operations are done. Let's look into the other examples. So let's say we want to read node 5 in version 4. So our version 4 points to the brown color. So let's go here. So we come here and we saw that here left is pointing to the node 5. Node 5 actually is this old node, black color node. But as we are reading the version 4, and for version 4 we have an entry for left pointer in modification box. So instead of picking up this, we just pick whatever is new modified value in the modification box, which is node 5 dash. So node 5 dash will point to this green node, right? So we'll come here, and here we see the version 4, the value is 20. So we will return 20 as the answer. So I know it's a bit complicated, maybe you can watch it again and then you will understand, but that's how this strategy is implemented. So by the time you have now understood a few problems in this kind of approach, so as we started with the BST, right? But at the end, in the latest version, let's say you see the root node has a value 10, but the left pointer has a value 20 and 30 as well. So it's not a BST anymore. So it's difficult to implement this kind of approach in BST. So when you are implementing such an approach in BST, right, you have to handle invalid operations as well. So in this example, I'm not handling them for the sake of simplicity, but you cannot put a value which is larger, which is greater than the node to its left, right? So whenever you are making an operation like that, you have to throw an error and saying invalid operation or something like that. So such scenarios you have to handle as well. Otherwise, it will not be a BST anymore. So this is one of the issue with it. Another issue, if you can look into, is like with the modification box 1. So as we have the size of modification box 1, after the modification box is full on a root node. So initially it was empty, then it became full here, right? So after the modification box is full, for every change in the path, either in the root node or in the child node, we have to copy it again and again. So here, when we were making change into this node 5, we have to copy a root node as well, right? So now another change in this child is leading to a copy of both the nodes again, right? So as the modification box is size is 1, so when we copy the node, by default the modification box become full. So what do I mean here? So whenever we are copying a node, for example, we copy this node and we get this new node, right? So whenever we are copying this node, the new changes we put into the modification box and we apply the changes in the previous modification box, right? So as as the size is 1 and every new change we put into the modification box, so it by default becomes full, right? So any new change in this node will lead to the copy of it. So we don't keep the size as 1 in real world scenarios. We keep it as minimum 2, 3 or 4. So that is the problem with modification size 1. So it's not a valid BST now. So if you want to prevent it, you want to keep a valid BST here. So ensure new values are inserted or updated and they obey the rules of BST, otherwise throw the error. This makes the implementation a little bit complex, but that's the thing here. Benefits. So if you keep the modification box sizes like genuine size, not 1, then the updates just add a mod entry. You don't need to copy the whole node and do all the modifications, which is just the constant time. So it's beneficial in such cases. Nodes are copied only when the modification box is full, and this avoids full path copying. For example, if your modification box has some space, for example here, so it was having some space, right? So we just added the value in the modification box. We didn't copy until the root, right? So this you can prevent here if your modification box has space. Multiple versions uses unchanged nodes, which saves memory. So as we can see, we were reusing this node in all the versions, right? Because we were not updating any value here. So we reuse whatever is not getting changed. You can access all the past versions efficiently, but only the latest version is writable here. So you can access all the versions, but you can only write a new version here, because you don't have all the version history with yourself. So as you can see, in this particular node, you have only the information about version v5, and but for v5 you can say the value is 30, but for v4, v3, v2, v1, for all these 4 versions, the value is not 20, right? So for v1 the value is 5, then there is a value 8 as well for v3. So you, by looking into this node, you cannot predict the value for all the versions. You have to go to the root node and follow the rules to find out the value for a particular version. So writing the older version is not possible here. Version info is stored in the node, so no external version tracking is needed for all the nodes. Especially useful when the structure is updated infrequently and shallowly. So it's very useful when you are not making regular updates there. Your updates are rare. Limitations again here is like complex traversal. Implementation is complex, traversal is complex. You have to look into the modification box, then decide which value you want to take. So the traversal and as well as the implementation is complex. And the version aware logic is everywhere actually. It's not in the only in the mapping or in the root node. Every node will have a version info. So as you can see here, it says the version 4 information here is here in this node as well. You have a version information in this node as well, and same for all the other nodes. Plus you need to keep a track of root node in all the versions, right? So this is some extra headache you have to take care of. Rules of the BST can be violated, that I've explained clearly, and poor fit for highly dynamic or balanced trees like AVL and redback trees, because in AVL and redback trees change the structure of the tree, right? So AVL and redback trees are used for balancing trees, like so that the tree does not get skewed, right? So you have to shift the pointers heavily there. So that is not this approach is not very good fit for those kinds of trees. For detail you can look into this trees actually. So for graphs as well, number of mod boxes per node grows within degrees, so it's not a good fit. So as in graph actually, a node can point to many other nodes, right? And many nodes can point to the same node. So as the number of degrees in the graph increase, the number of mod boxes also increases. So if you want to take this approach there in the graph, it's not good, it's not a good fit there, because their modifications are huge. Because here in the tree, you know that root node will point to two nodes at max. So in binary tree it points to two nodes, in ternary tree it points to three nodes. So you have some number there, but in graph there is no number. N nodes can point to one node, and one node can point to n nodes. So it's difficult to implement there, it's not a good fit there. So use it when you want to keep the past states of the tree with minimal overhead. The overhead here is minimal with the large modification box. So it's overhead here, it's looking large because I've kept the modification box size 1, but with the modification box size 3, this example will be really small. So the mapping here will be reduced by a lot, and useful for logging rollback and undo operations, and not ideal for AVL trees, redback trees, and segment trees, and all those things. So I hope that was clear to you. Let's look into another approach, which is copy on write, which is a simpler approach. So in the read operations, in this kind of approach we just copy when we are making any modifications. So in the read operations, there is no change happens while doing the read operations. So let's understand it while taking the example. So let's say we are creating a tree, version 0. In the version 0 we are inserting a root node 10, so it's there. Now we are inserting inserting a node 5 in version 1. So let's say 5 will go to the left. So whatever we come across while writing, we copy that. So for inserting a 5, we first go to the root node, right? So this comes into our path, we copy it. Then as you can see, the left is null, so we just created a node 5 and pointed to 5. Now insert 15 in the latest version. So whatever comes to our path, so 10 again comes to our path, we copy it, and the right pointer is null, so we create a node 15 and point it to it. Now we insert 3 in version 3. So we are making update in the latest version here again. So we come to this node, it's coming into our path, we copy it, we go to the left, this is coming to our path, so we copy it as well, and then again go left, which is null, so we create a new node 3 and point it to here. As you can see, the previous nodes are being reused. I'm representing it by different colors, pointers. So here the 5 was being reused by the version 1 and version 2, and here as you can see 15 is being reused by version 2 and version 3. So older nodes here which are not changing are used here as well. We do not copy the whole tree here as well. So it looks something like a path copying, but it's a bit generic here. So in path copying, you make an update to a node, and whatever is coming to a path will copy the whole thing. So but here it's more generic. So path copying is usually used in trees like segment tree, and it is usually used for trees, but this can be used for any data structure like linked list, nodes, stack, array, and all. So whatever you come across, you copy that part and you would use else. So it's a more generic approach of path copying approach. So the same thing I have written here. The path copying is usually used in trees, which is persistent BST, segment tree, and functional data structure. But copy on write is a more general approach on any mutations. So for any mutations, you just copy whatever you are mutating and use the rest. So used for both trees as well as flat data structure, array memory pages and all, often seen in system level structures. So it's used by Linux and file systems to maintain version histories and all. It's a lazy approach. You copy when you made only a write. Whenever a write occurs, then only you copy. So it's a lazy approach. For array, you either have to copy the whole array, because it's not possible in array to copy a particular value, right? So either you have to copy the whole array, or you just a tree based structure for it. So benefits here are: all versions remain unchanged, perfect for undo, redo, such type of operations, and all readers can simply access old versions without locking. So there is no locking required, because you need to maintain this root node for different versions, but all the readers can access any version. There will be no conflict occurs here. Okay, each writes give you a clean updated copy, no side effects on the previous data. So any write will not touch any previous data, right? So you create a new node for every write, right? So there is no side effect here. In operating system like Linux, both processes like share memory until you write occurs. So it's usually used in Linux and operating systems, and it's used for processes when they share memory. So as you can see here, let's say if you will look these nodes in terms of memory, let's say this is a memory which some processes are sharing. So it's used to find out which processes you, how many processes shared this memory. So it's used for that purpose in Linux, and it's efficient there. Limitations here are: full copy per update is slow and wasteful for large arrays. So arrays, as you know, you have to copy the whole array. So you cannot use it for very large arrays. You can only use it for small arrays. So if you are using it in tree or paste copy and write arrays, then it's complex to build from scratch. You have to manage the version pointers of the root. So all these pointers you have to manage explicitly. Watch what version points to what node. You have to manage it explicitly here. So with trees, with frequent updates, it can be costly. So if you are making frequent updates on a tree, so you will be having many versions, and you have to copy many nodes here, right? So with frequent updates, it can become costlier in trees as well. So let's quickly look into this remaining approaches. I'll just explain it in short. So snapshotting is what you must have in AWS or something like that. So it's like taking a snapshot itself. For example, let's say you have an array. Initially version 0 is 123. Now you want to update index to value 99. You just take the snapshot. Snapshot is basically like copying the whole array. It's like copy on write, but here if you are using it on tree, right, you have to just copy the whole tree. It's the very basic approach. Copy the entire data structure and make the update. So you just manage the version. You just keep the track of version, and you copy the entire data structure and create a new version. It's simple to implement, but it will take a huge amount of space. It's simple to implement. Older versions are untouched. They are still safe to read. There are no update happening on the older versions. Also, the nodes in the older version are not getting reused here as well. So that's one of the limitations. So you can go to any previous snapshot easily, and every past state is 100% available and not approximately. Limitations here: full copy, no sharing or optimization on space, slow updates for larger data structure as you are copying the entire data structure. Most of the data may be unchanged but still getting copied. So when you are looking into this array, right, so these two entries were not changing, but still they were getting copied. So it exhausts memory quickly, as you can see. So there is another approach, which is log structured data structure. Instead of modifying the data structure directly, we log every operation here. So here we do not make any changes in the data structure. We just log everything. So to read a version, we replay the log, and to update, we just append a new log there. So let's see a small example for this. So let's say we have an array with 000. Now for every update, we just log it. So for example, we have a update operation where we want to change index 1 to 5. We just log it, set 1 to 5. Then we are updating index 2 to 8. We just log it. And then again we are changing the index 1 again to 9. We just log it. We are not changing the actual data structure, we are just logging everything. So to reconstruct all the versions, right? So let's say you want to know how your array look like in version 2. So you just replay the logs until version 2. So this indexing here, these numbers here will represent the version 2, and this just represents the operation. So you just replay your logs until version 2. So you set the value of index 1 to 5, then index 2 to 8, and you just return the updated array, which will be 1 to 5 and index 2 to 8. For version 2, you will just replay all these logs. So you will update the index 1 to 5, index 2 to 8, then again index 1 to 9. This you return that array. So you have to keep whatever you do, what for any version, you just take the initial data structure, tree or array, and you perform all the operations up to that version from the logs, and you just return that version. That's how you implement this type of data structure. So it's immutable and thread safe because we are just appending everything in the logs. We are not overwriting anything. So it's memory efficient because whatever we are changing, we are just logging that. We are not logging anything extra. We are not copying anything or something like that. So it's memory efficient. So it's auditable and debuggable because you can see literally every change you made in the data structure at any time. So as you are logging any change here, you can just find out what all changes were made into the data structure. So it's very easy to debug. Time travel is possible here because you can easily go to any state from the logs. And for efficiency and for performance improvement, you can just batch the logs. For example, after version 3, the value of this index 1 will be 9, right? So you can just batch them. So instead of updating index 1 to 5 then to 9, you can just directly update it to 9. So you can batch the logs accordingly. Limitations are reconstructing from logs will take time because you have to replay the logs every time. So logs can grow by a lot actually. So as you keep on updating your data structure, your logs will grow. So after some time, you might want to prune some logs, prune some older logs and delete some older versions. Implementation is complex because you need to manage your logs version and you have to implement for replaying and everything. So implementation is complex. Snapshotting on every update will exhaust. Okay, this is not the point here. I just delete it. I think I copy pasted it from the previous approach. So this is being used in databases. So database changes all the database whenever a database make a change, it just logs it for debugging purpose. So it's used by database and it's used for debugging and auditing tools. They use the same thing, and it's used by UI time travel as well. So if you have worked with the Redux, right? So there is a called there is a Redux tool that you use in the development. So when you make a update in the UI, you can just go back to any previous version of the UI if you are using that tool, right? So it's like that only. So it's used for replaying UI events. That's all for this video. I hope you like this. Please like, share, and subscribe the channel. Thank you.